today we have a lot to do. We've got about 44 minutes to get through it. I'm not sure how we're going to do it, but we will try. Okay, we want to talk about motors, generators, and electromagnetic induction. This is the culmination of this whole quarter. Today, what we're going to talk about really is why we've been studying this stuff, because it ties together electricity and magnetism, and it is the foundation for modern civilization as we know it. 99% of the electricity that you use is created this way, and that's what I want to talk about. Okay, so I have first. Let's look at a problem here. Straight wire in a magnet. It feels an upward force. Let's practice that second right-hand rule and figure out which pole of the magnet is that. Is that the north pole or the south pole of the magnet?
North.
Okay. Now, instead of having a straight wire, let's look at what happens if I make my wire a loop. So now the current's going one direction. What direction will this side of the loop feel a force? What? Up. And what direction will this side of the loop feel a force? Down. Okay. So what will that loop of wire want to do? Not spin. It's not going to spin completely. Okay. Well, look at the answers A, B, and C. Which one of those is a possibility? Okay. Does it make sense it's going to rotate clockwise? If I don't do anything to it, how far will it rotate clockwise? 90 degrees. Because think about that. If once it rotates so that, let's see, this one's going into the board, and this one's coming out of the board, the force here is up, the force here is down, and that's all it's going to do. Right? Remember that. We're going to talk about that in a little bit. But also, now, this is an interesting little device. We can do a lot of things with this. So imagine for a second that I created something just like this. I attached a spring right here, okay, so that it doesn't want to rotate clockwise. The spring wants to bring it back to equilibrium. And then I put a little needle on it with some numbers. What would this device tell me? How much current is flowing through that wire, which we call an ammeter, okay? Because the more current, the more it's going to want to twist. Remember, force is proportional to current as well as magnetic field strength. And so, and the spring wants it to come back. So if I have it all calibrated, I can measure how much current's flowing through that wire by how much it twists, okay? That's the basic ammeter design, okay? They're talking about it right there. All right, but let's continue on. Here's another loop of wire. Same idea, just a different drawing, okay? Now notice I've got a nice rectangular loop of wire. The current, let's say this is positive end of our electrical circuit. This is negative end. So the electrical current's going in and out. Here's my magnetic field going from left to right. So this would be the north pole. This would be the south pole. Can you all agree that this end of the wire is feeling a force into the page, and this end is feeling a force out of the page? You can try it with the right-hand rule if you want to, okay? Right, boom, boom, into the page, boom, boom, out of the page. And this side, see, here's positive, here's negative. So here the current's going up, and on the right-hand side it's coming down, okay? So just like before, this thing's going to want to rotate. And it will rotate until this end of the loop is at the top, and this end of the loop is at the bottom. You with me? Good so far? Now, if I had a way at that very moment to flip the current and change it so that in this end of the loop it was now going in, and in this end of the loop it was coming out, it would rotate. Because notice it has motion going this way. It's got some inertia, so it's going to keep going that way, and then it's going to spin. And then if I flip it again and again and again, it's going to rotate and rotate and rotate, and I will have developed a thing that we call an electric motor. Okay?
Goes all the way around because it's already turning.
It's already turning, so it has some inertia. It's going to continue that direction, and then it carries it past. If it was perfectly at equilibrium, yeah. If it was perfect, it wouldn't even do anything really. But you keep switching it. You keep flipping it at just the right time. This is a very basic diagram of an electric motor, you guys. Okay, you take a coil of wire. You place it in a magnetic field. Okay, you have a device here so that as my coil of wire rotates, it rotates this axle, which has the connections on it that are connected here and here to my electrical source. Notice this is the positive terminal, this is the negative terminal. These things, which are called brushes, don't move. But as the axle rotates, notice that this one is connected to this end of the loop, this one is connected to this end of the loop. Right now, this end of the loop is the positive terminal, this end of the loop is the negative terminal. But as this thing rotates, this part of my loop will come into contact with the other brush. And this part will come into contact with the other brush. So the current will flip in the armature. The current will flip at just the right time so that this thing can continue to rotate. Okay? I think I have a better picture of it here. All right? So I have an electrical source. It's attached to brushes. This armature has more coils of wire is better than just one coil. And that armature is connected to an axle that has this thing called the split ring commutator because it's a ring that's split. So as it rotates, it'll reverse which electric electric terminal it's attached to, so it reverses the current at just the right time. This thing continues to rotate. You put a little blade on it, you can fly an airplane, you can cool yourself off, you can put a blade on it, you can make a blender, you can put a wheel on it, make a Prius, you can do all sorts of things, okay? This is how we take electrical energy and turn it into mechanical energy. It's an electric motor, okay? It's the whole purpose. And if you really think about conservation of energy here, how does the battery get its energy? Chemical energy, which is turned into electrical energy, which is then converted to mechanical energy. It's kind of cool, okay? Okay, so with electric motors, you guys, there's a couple of parts that you need to be aware of. You need to know what the armature is. That's the piece with the coils of wire, okay, that rotates. You need to know what the brushes are and what their function is. They are the electrical contacts that stay stationary. And then the split ring commutator. What's the purpose of the split ring commutator? To switch the current at just the right time so that it continues to rotate. Okay, that's what the split ring allows the current to flip at just the right time so that the armature will continue to rotate. That is the armature is the piece that has the coils of wire that's in the magnetic field. The brushes are the contacts, the electrical contacts with the split ring. Yeah, that are stationary. Okay. Let's imagine we're going to talk about electromagnetic induction now, and this is related to electric motors, and this is everything. Okay. So imagine I took a wire, not a current-carrying wire, just a plain old wire, and I moved it in a magnetic field. Okay. That wire has electrons in it. Would those electrons feel a force? Yes. Yes, they would. Okay, good. So, right. So the electrons will feel a force, and this will basically generate a potential difference in my wire. Okay, it'll create a positive end and a negative end in my wire. So far, so good? Steve made a good observation. If you move it the other way, the electrons will try to move the other way. So I can move it back and forth, and I can get my electrons to jiggle back and forth if I wanted to, creating something like, I don't know, alternating current. Okay? Okay. All right? There is an equation. There it is. If I want to figure out how much of an EMF I generate, remember that EMF stands for electromotive force, which is basically just potential or voltage that you create rather than use. If you want to figure out how much potential you create, it's equal to the strength of the field times the speed of the with which you move the wire times the length of the wire that's in the field. Let's talk briefly about Michael Faraday. Excellent, excellent experimenter in the realm of electricity, made some incredible discoveries, came up with some laws of electromagnetic induction, which still hold true today and really explain electricity and magnetism very, very clearly. He discovered this relationship basically simultaneously with another physicist, but they weren't working together. Joseph Henry, I believe, was an American. They both made the discovery at about the same time, but Faraday got his published first, and he is therefore credited with this discovery. Here's what Faraday did, okay? He was a pretty smart guy, and here was his idea. Ooh, not there. There. This was kind of cool. Think about this setup for a second. He's got a battery. He's got a circuit with a switch in it. He created a, what's this called when you wrap a loop of wire? Solenoid, which makes a magnet, right? And particularly if you put an iron core in it, it makes a good, strong electromagnet. So he made an iron core, a little solenoid. If he closed this switch, this left-hand circuit, this X circuit, would basically just generate a magnet, right? Because the iron core is circular, what it will do is it will actually kind of it'll what's the word I'm looking for? It'll trap the magnetic field. It'll direct the magnetic field into a circular motion. So he's basically creating this little electromagnet. And did I draw the magnetic field direction right? Let's practice right-hand rule number 3. The conventional current's going from positive to negative, so therefore it's looping this way. I drew the magnetic field the wrong direction. Okay? Can you see how it's looping this way? So the magnetic field inside is actually going that way, for what it's worth. But so he was thinking, cool, I can make a magnetic field. And I know because Hans Christian Ørsted, discovered that a magnetic field or an electricity affects a magnet, then maybe a magnet should affect electricity. So if I create a magnetic field and I have another coil of wire attached to a ammeter, that I'm thinking that by using current to make a magnet, I can take that magnet and make more current. And I can show that I can use a magnetic field to make current, just like a current makes a magnetic field. You with me? He's awesome. He's got it all set up. He's ready to go. He closes the switch, and the needle jumps and then goes to 0. Oh, he's all bummed. Then he opens the switch, and the needle jumps the other way and goes back to 0. That's a bummer. I'm not making electricity. I thought I was going to. But then he stops and thinks about it. And he's like, wait a minute. I did create electricity when I closed the switch, and then I didn't. And then when I opened the switch, I created electricity again, and then it went away. What's happening right when he closes the switch? What's being created in this left-hand circuit? An electric field? Magnetic field. And right when you close the switch, what's happening with that magnetic field? Well, let's just think about it. When the switch is open, is there a magnetic field? After he closes it, is there a magnetic field? So what's happening right in between? Excellent. It's creating a magnetic field, right? The magnetic field is growing from nothing to something. When that's happening, the needle jumps. But when the magnetic field is constant, I know, that's my phone. When the field is constant, no current. When he opens the switch, that magnetic field goes from something to nothing, and the needle jumps the other way. And then when there was no magnetic field, it goes back to 0. So what did he discover? Okay, not only magnetic fields, but specifically a changing magnetic field will induce a current in a wire. Okay? And that is a huge, huge discovery. Let me demonstrate it to you here right now. Here's a picture of it. Basically, if I take a coil of wire and I have a magnet, notice that the magnetic field around this bar magnet is always going to look the same. But if I move the magnet, I will change the field in that wire, and I'll get current. If I move it the other way, I'll change the field in another way, and I'll get current the other direction. But if I leave the magnet stationary, no current. Yeah? Can kind of visualize that? So here's what Faraday discovered. That I can induce a current in a wire if I move the magnetic field relative to the wire. I could just as easily keep the magnet stationary and move the wire if I want. Either way, but as long as there's a changing magnetic field, I will induce a current. And here are the things that affect how much current I get. You already probably know some of them. Okay? The speed with which I change the field, that will affect the current. The strength of the magnet. A stronger magnetic field will create a greater current. The number of loops of wire I have will affect how much current I get. The area of those loops. A bigger area will tend to generate more current. And finally, the angle of motion. If my field is perpendicular to the plane of my loops, I will be able to generate more current. So then we come into this concept. This is one of the coolest words you're going to learn in physics, I think, because it just sounds neat. People like to use it. And that is flux. Okay, flux. It just sounds fun to say. The flux capacitor we talk about. That's how we get back to the future. And all sorts of good things. Okay, magnetic flux is represented by the Greek letter phi. And the idea of magnetic flux, what you need to think about conceptually, is the number of magnetic field lines that pierce an area or pierce a loop. Okay, so if I have a loop of wire, I have a certain amount of field lines going through it. I'm going to call that concept flux. Okay, so think about how we can measure the flux. What factors are important to measure the flux, the number of field lines in a loop? What are the things that will affect that? okay, which would be the strength of the field, right? Okay, so strength of the field. What else would change or determine how many field lines I have in an area? That's what we just said, the strength of the field. The area of the loop, excellent. And there's one other key factor.
How about the strength?
That's the strength of the field. Strength of the field, area, and what about the orientation? Right? Okay? Excellent. So magnetic flux can be determined by three things. The strength of the field, the area of the wire, and the angle between the loop and the field. There's our equation. Flux equals BA cos theta.
Calculate area of
Normal to the loop. So we measure the angle relative to a normal to the loop, or a perpendicular line drawn to the loop. Now, I talked about how you can get more current if you have more loops, right? This is just the flux through one loop. If we have more than one loop, we call it not a flux capacitor. That'd be really cool, but we don't. We call it a flux linkage, And so we add one more factor to our equation, which is N, and it becomes like a basketball thing, NBA, cosine theta. And N is just the number of loops you have of wire. And this is called a flux linkage. It'll induce more current. Okay? Everybody good with that kind of? Conceptually, what we're talking about in terms of flux? All right. So here's kind of a picture of it. Okay? There's some field lines just traveling through space. Those are magnetic field lines. There's a square loop. The flux would be basically the amount of magnetic field going through that loop. And it would change in a variety of ways. I could change the flux by changing the strength of the field, by changing the angle between the two, or by changing the area of my wire. Yeah? Great. Actually, there's another way, too. If this was all my field was these four lines, I could just move it out, and that would change the flux. I'd have a decreasing flux by pulling it out. I'd have an increasing flux by pushing it in. Okay? Faraday's law of electromagnetic induction says that the EMF you generate is equal to the rate of change of flux. The rate of change of flux. How fast the flux changes is what creates your voltage. Okay? The negative sign, don't worry about. Everything else, think about. If you have flux, you have magnetic fields in a wire, how quickly you change that flux determines how much current you get. All right? So let's think about this a second. This is how we generate 99% of the electricity that you've ever used in your life. All right? The civilization, or the society on which our culture is based, which loves electricity, this is it. We need a wire, we need a magnet, we need to change some flux. And that's what we do, okay? How can we change that flux? We can change the magnetic field strength, we could change the area of my wire, or we can change the orientation of my wire relative to the field, right? Lo and behold, this is what we do. Okay? This looks a lot like a motor, but it's the opposite. In a motor, this would be a battery, but now we have a light bulb. In a motor, the battery would cause the coils to turn, which we could use to do stuff. But now, if we can cause the coils to turn, we can make electricity to light a light bulb. Because by rotating the coils, I'm constantly changing the number of field lines going through those coils. I'm constantly changing the flux. Does that make sense? This is an electric generator. It's like a motor in reverse. Okay? Again, the same picture we had before. This looks a lot like that electric motor, but this is an electric generator. We turn the coils generate electricity to light the light bulb. Excellent. This is like the hand-powered radios. Now, if we get tired of turning it, we try to figure out some other way to turn it. Let's attach a blade to it and put it up in the wind and let the wind turn it. That would be a windmill. Let's build a big dam and store water and let the potential energy of that water fall through the dam to turn a turbine, which is a coil of wires in a magnetic field, and to make electricity. Or better yet, let's boil water and let the steam turn a turbine to turn coils in a magnetic field to make electricity. How can we boil that water? We can burn coal. We can burn natural gas. We can burn oil. We can burn nuclear fuel. A nuclear reactor is really just a fancy way to boil water to turn a coil in a magnetic field to make electricity. That's it. 98, 99% of all the electricity in the world is created by turning coils in a magnetic field. Okay? The other 1% are photovoltaic cells. That's the only other way that we know of right now to make electricity, and that's totally different, and it's a very minute percentage of the world's electricity. That's different. Different, okay? All right? Isn't that cool? That's kind of cool, I think. Okay, so this is basically what an electric generator is. And if you think about it, an electric generator, when you rotate that coil, the current is always going to be going one way and then the other way, one way and then the other way. That's what we call alternating current, or AC current. This is one of the reasons we use AC current, is because that's how we generate it. The other reason we use AC current is because it's easier to change voltage in AC current. And remember, when we transmit electricity, we like to transmit it at high voltages. Okay, DC current is just direct current. That's what comes out of a battery. Finally, there's this thing called Lenz's law. He's the guy that made his law. Okay, good question. Okay, and here's Lenz's law in a nutshell. It's kind of like magic. Ooh, I almost knocked over my flower. That would be bad. Okay. Okay, so here's Lenz's law. The current will be in such a direction, the induced current, the current that you create will be in such a direction as to oppose the change in flux that created that current in the first place. Okay? It's kind of like equal and opposite reaction. It's definitely making sure we don't violate the law of conservation of energy. And it makes sense when you think about forces and conservation. So there are questions that deal with Lenz's law that are incredibly complicated. You will have to think hard and long about, okay, is the flux getting stronger or weaker? What direction is it getting stronger or weaker? Therefore, what direction will current be created so that it opposes that change? Okay, that's how you deal with Lenz's law. What else do we have on here? There we go. We can stick on that one for a second. Well, let's think about this for a second. Okay, let's try to apply Lenz's law. We'll just try it real quick, and then we'll be done. And I have a couple of generators if you want to see how we can generate electricity. Let's look at this situation on the right, left. By right, I meant left. Okay. First of all, let's look at this bar magnet. What direction is the magnetic field that's... Don't come in, guys. Okay. What direction is the magnetic field that's in my loop? Or what direction is the flux? Just in this loop, what direction is the magnetic field going? Up. Can you see that? It's going up, right? As I move the magnet up, does the upward field get stronger or weaker? When I'm moving the magnet up, towards the loop, from below. So as it's getting closer, the field is getting stronger in the upward direction, correct? The upward flux is increasing. What Lenz's law says is that the direction the current gets induced must therefore create a downward increasing flux to oppose that. So here's our third right-hand rule. That means the current will go this way around this loop so that it creates a field that opposes the change that created it. Yeah? Let's look at this one because it's a little bit trickier. What direction is the flux? Up. As I move the magnet down, does that flux get weaker or stronger? Weaker. Lenz's law says the current will be created to oppose that change. So Lenz's law, the current will be created to create an upward field, since the upward field is getting weaker. You with me? So it's going to go this way, creating an upward field. All right? That's Lenz's law. Okay. Yes. And if you guys need